You've seen the universe through telescopes. You've marveled at distant galaxies, nebulae painted across the cosmic canvas, stars scattered like diamonds on black velvet. You think you understand what brightness means in the cosmos. You think you know what power looks like when matter and energy dance together in the void. You're wrong. There are objects out there so luminous, so incomprehensibly brilliant, that a single one outshines entire galaxies containing hundreds of billions of stars. Objects so energetic they make our sun look like a dying ember. Objects that shouldn't exist according to everything we thought we knew about how the universe works. And for decades, we had absolutely no idea what they were. Welcome back to Echoes of Deep Time. Tonight we're going to talk about quasars, and I need you to understand something right from the start. This isn't going to be a comfortable journey, because quasars represent something that challenges our fundamental relationship with reality. They're beacons shining from epochs so ancient that the light reaching your eyes tonight began its journey when the universe itself was barely recognizable. They're monsters feeding on matter at rates that defy physics. They're engines of destruction and creation operating at scales that make our entire conception of power seem quaint, and we discovered them completely by accident. Let me take you back to 1960. The world is different then. The space age is just beginning. We're putting the first satellites into orbit, dreaming of reaching the moon. And astronomers are doing what they've always done, mapping the sky, cataloguing the stars, trying to make sense of the cosmic architecture surrounding us. Radio astronomy is new, exciting, revealing an invisible universe we never knew existed. Radio telescopes are picking up signals from across the cosmos, and astronomers are working to match these radio sources with visible objects in the sky. It's tedious work. You take a radio coordinate, you point your optical telescope at that position, and you see what's there. Usually it's a galaxy, sometimes a star, occasionally nothing you can identify. Routine observations, the kind of grinding, systematic science that rarely makes headlines. Then someone points a telescope at a radio source designated 3C273. 3C stands for the third Cambridge catalogue of radio sources. Just a number in a list, just another target to check off. The optical telescope finds what looks like a faint blue star. Nothing remarkable. Except this star is also an incredibly powerful radio source, which is strange. Stars don't usually broadcast radio waves with that kind of intensity. But okay, it's weird. The universe is full of weird things. You make a note, you move on. Except some astronomers don't move on. They become obsessed with these odd radio-loud stellar objects. They're cataloguing more of them now. 3C48, 3C196, 3C286. Strange blue points of light that look like stars, but behave like nothing they've ever seen. They're trying to take spectra, to break down the light and see what these objects are made of, how hot they are, what elements they contain, and the spectra make no sense. Imagine you're a spectroscopist in 1960. You know what stellar spectra look like. You've seen thousands of them. You understand the patterns, the absorption lines that tell you about temperature, composition, stellar type. You have decades of experience reading these cosmic fingerprints. And then you look at the spectrum of 3C273, and it's gibberish. The lines are in completely the wrong places. Nothing matches any known element or any known temperature. It's as if someone handed you a book in a language that uses familiar letters, but arranges them in ways that form no recognizable words. For 3 years, astronomers stare at these spectra and understand nothing. Then, in 1963, a Dutch-American astronomer named Martin Schmidt is looking at the spectrum of 3C273 for probably the 100th time, and something clicks. He recognizes the pattern of the lines. It's the Balmer series of hydrogen, the most fundamental spectroscopic signature in astronomy, the thing you learn about in your first astrophysics class. Except the lines aren't where they should be. They're shifted, massively shifted, pushed toward the red end of the spectrum by an amount that seems impossible. Schmidt does the calculation. His hands might have been shaking. The red shift is 16%. 16%. That means this object is receding from us at 16% of the speed of light. And if Hubble's law applies, if distance and recession velocity are related the way we think they are, then this star isn't a star at all. It's not even in our galaxy. It's 2 billion light years away. Let that sink in for a moment. 2 billion light years. The light Schmidt is analysing left this object before the first multicellular life evolved on Earth, before the first fish swam in ancient oceans, before the first breath of oxygen was exhaled by primitive algae. And this object, at that incomprehensible distance, is bright enough to photograph as a point of light with 1960s telescope technology. Do the math. If something is that distant and still that bright, the actual luminosity, the total amount of energy it's radiating, must be staggering. We're not talking about the brightness of a star. We're talking about something outshining an entire galaxy. One object, brighter than 200 billion suns combined. Schmidt publishes his findings. The astronomical community reacts with skepticism, confusion and excitement in roughly equal measure. Because if this is true, it breaks things. It breaks our understanding of what objects can exist in the universe. There's no known physics that allows a single source to produce that much energy continuously. No star can do it. No cluster of stars can do it. Even if you packed 1 trillion stars into a tiny volume, you couldn't explain this brightness. But the observations don't lie. Other astronomers verify the redshift. They find more of these objects. Each one is impossibly distant and impossibly bright. Someone coins a term, quasi-stellar radio source. The name gets shortened, compressed into something catchier, something that sounds almost cute despite describing some of the most powerful phenomena in the universe, quasar, and now the real work begins, because naming something doesn't explain it. Having a label for these cosmic monsters doesn't tell you what they are, how they work, why they exist. The late 1960s and early 1970s become a golden age of theoretical speculation. Papers proliferate, ideas multiply, some brilliant, some bizarre, all trying to answer the fundamental question, what the hell are we looking at? The energy problem is severe. You need to explain how a region of space, probably smaller than our solar system based on how quickly quasars vary in brightness, can output more energy than hundreds of billions of stars. You need a mechanism. You need physics that works. Some scientists suggest maybe quasars aren't actually that distant. Maybe the redshift doesn't mean what we think it means. Maybe there's some other explanation, some exotic physics that can shift light without requiring recession velocity. It's a tempting idea. If quasars are closer, they don't need to be as luminous. The energy problem becomes manageable, but the evidence keeps mounting that no, they really are that far away. Their redshifts correlate with their other properties exactly as Hubble's law predicts. Some astronomers find the faint, fuzzy host galaxies surrounding quasars, confirming they're extragalactic. The distance is real. The brightness is real. The energy problem is very, very real. Other ideas emerge: matter-antimatter annihilation, supermassive stars collapsing, exotic physics involving white holes or naked singularities, chain reactions of supernovae. Each theory has problems. None quite works. The universe has presented astronomers with a puzzle that resists every solution they propose, and then someone mentions black holes. Now, black holes in the early 1970s are theoretical curiosities. Einstein's equations predict them, sure, but nobody's certain they actually exist. The term black hole itself was only coined in 1967 by John Wheeler. The idea still seems like science fiction to many physicists. Objects so dense that nothing, not even light, can escape their gravity. Regions of space-time so warped they're essentially removed from the rest of the universe. It sounds absurd. But desperate times call for desperate measures, and quasars are nothing if not desperate times for theoretical astrophysics. Someone, actually several people independently, proposes the following. What if there's a black hole at the centre of a quasar? Not a stellar mass black hole, the kind that forms when a massive star collapses. We're talking about something much bigger. Millions of times the mass of the Sun. Billions, perhaps. A supermassive black hole. And what if matter is falling into this black hole? Here's where the physics gets interesting. When matter falls toward a black hole, it doesn't just drop straight in like water down a drain. It spirals. It forms what's called an accretion disk, a swirling maelstrom of gas and dust and shredded stars orbiting the black hole before their final plunge. And as this matter spirals inward, something remarkable happens. It heats up. Gravitational potential energy converts to kinetic energy. Friction between particles in the disk generates heat. The inner regions of the disk, orbiting at significant fractions of light speed, reach temperatures of millions of degrees. At those temperatures, matter doesn't just glow, it screams. It radiates across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, and here's the beautiful, terrible thing. This process is efficient, hideously, remarkably efficient. When matter falls into a black hole via an accretion disk, about 10% of its mass energy can be converted into radiation. 10%. For comparison, nuclear fusion, the process that powers stars, converts less than 1% of mass to energy. Einstein's equation, E equals mc squared. Mass is energy, and when you're feeding a supermassive black hole, when you're dropping the equivalent of several stars per year into a gravitational maw, that 10% efficiency translates to obscene amounts of power, enough to outshine galaxies, enough to explain quasars. The math works, the physics works. Suddenly, quasars make sense. But understanding the mechanism doesn't make them less terrifying. If anything, it makes them worse. Because now we know what we're looking at. We're watching black holes eat. We're observing the universe's most efficient engines of destruction in action. Every photon reaching us from a quasar was born in the final, screaming moments of matter's existence before it crossed the event horizon and ceased to be part of our reality. Let me paint you a picture of what's actually happening at a quasar. Start with the black hole itself. It sits at the centre, invisible, defined only by its absence. Its mass might be 1 billion times that of our Sun, compressed into a volume smaller than our solar system. The event horizon, the point of no return, would be larger than the orbit of Neptune. If you could somehow place our Sun at a safe distance from this monster and watch, the Sun would be a tiny spark next to this abyss. Around the black hole, the accretion disk extends outward. Near the black hole, in the innermost stable orbit, matter is moving at approximately half the speed of light. At these speeds, relativistic effects dominate. Time dilates, space contracts. The disk itself warps the fabric of space-time, dragging it around in the black hole's rotation. If the black hole is spinning, and they almost always are, this frame-dragging effect creates a region called the ergosphere, where nothing can remain stationary. Space itself is being pulled around the black hole like water circling a drain. The disk glows with the heat of infalling matter. The innermost regions shine blue-white, hot enough to emit X-rays. Further out, the temperature drops and the emission shifts to ultraviolet, then visible light, then infrared. But even the cooler outer regions are hotter than the surface of most stars. The entire disk is a tiered inferno, layered by temperature and orbital velocity, and it's not peaceful. The disk is turbulent, chaotic. Magnetic fields thread through the plasma, tangling and snapping in processes we still don't fully understand. These magnetic fields extract energy from the rotation of the black hole and the disk, channeling it into focused beams. Matter and energy, compressed and accelerated to near light speed, shoot outward from the poles of the black hole in jets that can extend for hundreds of thousands of light years. These jets are their own kind of horror. relativistic particles streaming through space at 99.9% of the speed of light. If you were in the path of one, and here I mean if your entire galaxy were in the path of one, the radiation would be lethal across interstellar distances. These jets punch through the surrounding gas, creating shock waves, heating intergalactic space, affecting the evolution of galaxies millions of light years away. The quasar's radiation doesn't just travel through space, it transforms it. In the immediate vicinity, within a few hundred light years, the intense ultraviolet and X-ray flux ionizes all the gas. Any molecular clouds that might have formed stars are torn apart. Any planets that might have harbored life are sterilized. The region around an active quasar is a dead zone, scoured clean by radiation that would make a supernova look gentle by comparison. Further out, the quasar's light shapes the structure of its host galaxy. The energy output can drive winds, massive outflows of gas moving at thousands of kilometers per second. These winds sweep through the galaxy, ejecting the raw material for star formation, potentially shutting down the birth of new stars across the entire system. The black hole is regulating its own food supply, creating what astronomers call feedback. It's eating so voraciously that its own radiation is blowing away the matter it needs to keep eating. This is the paradox of quasars. They're simultaneously the universe's most efficient engines and the architects of their own starvation. They shine so brightly because they're consuming matter at prodigious rates, but that very brightness pushes matter away, limiting how fast they can grow. There's a limit to how bright they can get, actually. It's called the Eddington limit, named after British astrophysicist Arthur Eddington, who calculated it in the 1920s, decades before anyone knew quasars existed. The idea is simple. The radiation pressure from all those photons streaming outward pushes on the infalling matter. At a certain luminosity, this radiation pressure exactly balances the gravitational pull. Any brighter, and the radiation would blow away the infalling matter faster than gravity could pull it in. The accretion would shut off. For a black hole of a given mass, you can calculate its Eddington luminosity. It's the maximum brightness sustainable over long periods. And here's the thing. Quasars are often shining at or near their Eddington limit. They're maxed out. They're operating at the absolute edge of what physics allows. Some quasars appear to exceed the Eddington limit briefly, which shouldn't be possible with our standard models. Either we're misunderstanding something about the accretion process, or these black holes have found tricks to circumvent the limit, perhaps by being highly magnetically dominated, or by having geometric configurations we haven't properly modelled. The fact that quasars keep surprising us, keep pushing against the boundaries of our theories, tells you how extreme these objects are. Now let's talk about what you'd actually see if you could somehow observe a quasar up close. And by close, I mean from a few thousand light years away. Far enough that you wouldn't be immediately vaporized, close enough to perceive the structure. First, you wouldn't see the black hole. That's definitional. Black holes don't emit light, but you'd see everything around it. The accretion disk would dominate your view, a spiral of light so bright you couldn't look directly at it even from thousands of light years distant. It would be a whirlpool of fire, rotating, turbulent, with patterns shifting on timescales of hours or days. The inner edge would glow with X-ray intensity, though your eyes wouldn't register X-rays. You'd just perceive an overwhelming brilliance at the centre, a point of radiance that hurt to contemplate. The disk wouldn't look like a simple spiral. Instabilities would create bright spots, regions where extra matter was clumping and releasing additional energy. These hotspots would orbit the black hole, creating a flickering, pulsing quality to the light. If you watched long enough, you might see larger disruptions, perhaps a star that wandered too close, torn apart by tidal forces and fed into the disk as a sudden surge of new fuel. The brightness would spike, then gradually decay over weeks or months as the stellar debris settled into its new orbital configuration. Above and below the disk, you'd see the jets. They'd appear as cones of emission, narrower near the black hole, expanding as they extended into space. Within these jets, you might perceive structure, knots of brighter emission, where the jet material was colliding with ambient gas, creating shocks. These knots would appear to move, sometimes faster, than light according to your observations, though that would be an illusion created by the jet's orientation and the finite speed of light. We call this superluminal motion, and it confused the hell out of astronomers when we first observed it. The region around the disk wouldn't be empty. There would be clouds of gas orbiting at various distances, some condensing and falling inward, others being blown outward by radiation pressure. These clouds would glow as the quasars' radiation ionized them, creating what astronomers call the broad line region and narrow line region, based on their velocities and distances. From your vantage point, you'd see a complex ecosystem of gas in various states of infall, orbit, and ejection, all responding to the gravitational and radiative forces of the central engine. And beyond all this, if you pulled back far enough, you'd see the host galaxy. Most quasars live in massive galaxies, systems that contain hundreds of billions of stars, but the quasar would outshine them all. The galaxy's starlight would be a pale backdrop to the blinding central beacon. Looking at a quasar's host galaxy would be like trying to see the faint glow of distant city lights, while someone points a searchlight directly at your face. This raises an interesting question. Why don't we see quasars in every galaxy? Our Milky Way has a supermassive black hole at its centre. We've observed stars orbiting an invisible point of mass in the constellation Sagittarius, and from their orbital dynamics we've calculated that this black hole, called Sagittarius A, has a mass about 4 million times that of our Sun. That's substantial. That's supermassive by any reasonable definition. So why isn't the Milky Way's core shining like a quasar? Why isn't our sky dominated by a brilliant point of light at the galactic centre, overwhelming the stars? The answer is simple. Sagittarius AI isn't being fed. It's starving. There's not enough matter falling into it to power significant accretion. The black hole is there, massive and patient, but without fuel it's dormant, dark, quiet. It occasionally snacks on a gas cloud or a star that wanders too close, producing a brief flare of emission, but these are tiny bursts compared to the sustained brilliance of an active quasar. This tells us something crucial. Quasars require two things to exist. First, a supermassive black hole. Second, a massive supply of fuel, and that second requirement is less common than you might think. For a galaxy to host an active quasar, something needs to funnel vast amounts of gas toward the central black hole. Just having gas in the galaxy isn't enough. Most of it is in stable orbits, or locked up in stars, or distributed too diffusely to accrete efficiently. You need a mechanism to remove angular momentum from the gas, to let it spiral inward, to deliver it to the black hole's doorstep. Galaxy mergers are one such mechanism. When two galaxies collide, and here we mean collide in the gentlest astronomical sense, as their stars pass through each other without actually impacting. Their gravitational interaction can disrupt gas clouds, creating shocks, compressing matter, removing angular momentum through tidal forces. Gas that was in stable orbit suddenly finds itself on trajectories that lead inward. The central black holes, if the galaxies each had one, begin receiving fresh fuel. They light up. They become quasars. This is why quasars are more common in the distant early universe. In the first few billion years after the Big Bang, galaxies were closer together on average. Mergers were more frequent. Gas was more abundant and less processed by stellar evolution. The conditions were perfect for feeding black holes. The universe was louder then, brighter, more violent. Today, galaxies are more spread out. Major mergers are rarer. Much of the easily accessible gas has been converted into stars or expelled from galaxies by previous episodes of quasar activity. The universe has quieted. Most supermassive black holes are dormant, lurking in galactic centres, waiting for the next meal that might not come for millions or billions of years. But when they do feed, When circumstances align to deliver fresh matter to a supermassive black hole, the transformation is dramatic. A quiet galaxy can become a brilliant quasar over astronomically short timescales, perhaps just tens of thousands of years, and once the fuel runs out or the black hole's radiation blows away the remaining supply, the quasar fades. The galaxy returns to a quieter state. The black hole returns to its patient waiting. This means when we look at quasars, we're seeing galaxies in a particular phase of their evolution. A temporary state, though temporary in this context, might last for millions of years. We're catching them at a moment of crisis and opportunity, when a black hole has access to food, and the galaxy's future is being determined by the balance between star formation and quasar-driven feedback. Let me tell you about variability, because this is where quasars get even stranger. In 1979, astronomers discovered something odd about a pair of quasars in the constellation Ursa Major. The two objects were very close together in the sky, just 6 arc-seconds apart, and they had nearly identical redshifts, meaning they appeared to be at the same distance. Their spectra were also remarkably similar. The odds of finding two quasars so close together with such similar properties seemed impossibly small, unless they weren't two quasars. A Princeton astrophysicist named Bohdan Paksinski, along with others, suggested that maybe this was a single quasar whose light was being bent and duplicated by the gravitational field of an intervening massive object. Einstein's general relativity predicts this phenomenon. Gravity warps space-time, and light follows the curvature of space-time, so a massive object between us and a distant light source can act as a lens, bending the light rays and creating multiple images. They called it gravitational lensing, and if this was an example of it, it would be the first ever observed. The proof came from watching the two images over time. Quasars vary in brightness. Their accretion is chaotic, and fluctuations in the rate of infall cause fluctuations in luminosity. If these were two separate quasars, their brightness variations would be independent, random. But if they were two images of the same quasar, the variation should match, except one image's variations would be delayed relative to the other, because the light paths have different lengths. They watched, they measured, and yes, the variations matched. One image changed brightness, and a few weeks later, the other image showed the same change. It was the same quasar, its light split and delayed by the gravity of a massive galaxy that happened to lie between us and it. The system is called Q1957Plofifan61, or the twin quasar, and it proved that gravitational lensing was real. This matters for more than just confirming Einstein's predictions. Quasar variability tells us about the structure of the accretion disk. If a quasar brightens or dims over a period of, say, one day, that tells us the region responsible for the variation can't be much larger than one light day across. You can't have a region the size of a solar system suddenly change in brightness coherently over a one-day timescale. The light travel time across the region would smear out any rapid variation. So when we observe quasars varying on timescales of hours to days, we know we're seeing processes occurring in incredibly compact regions. The engine producing galaxy-scale luminosity is operating in a volume smaller than the orbit of the outer planets. It's another way the physics of quasars assaults our intuition. That much power from that small A space, varying that quickly. Some quasars show periodic variations, regular oscillations in brightness that repeat every few months or years. These periodicities might be caused by binary supermassive black holes, two black holes orbiting each other at the center of a merged galaxy system, not yet coalesced into a single object. As they orbit, their gravitational interaction might periodically disrupt the accretion flow, causing regular brightness variations. Or the periodicity might come from instabilities in the accretion disk itself, patterns that form and repeat as matter spirals inward. We're still not entirely sure. Quasars, even after 60 years of study, keep presenting us with phenomena we don't fully understand. Let me tell you about polarization, because it reveals another layer of complexity. Light is an electromagnetic wave, and waves can be polarized. the electric field oscillates in a particular direction. Light from most sources is unpolarized, with the electric field oscillating randomly in all directions, but light that's been scattered, or that's been generated in magnetic fields, can become polarized. Quasar light is often highly polarized. This tells us that magnetic fields are playing a crucial role in the emission process. The polarization we observe comes from synchrotron radiation, charged particles spiraling in magnetic fields and radiating as they accelerate. The jets are full of this synchrotron emission. The accretion disk generates it. Even the broadline region shows polarization signatures that reveal the presence of strong magnetic fields organizing the gas flows. These magnetic fields aren't just passive bystanders, they're active participants in the accretion process. Magnetohydrodynamic turbulence, the chaotic churning of magnetized plasma, is probably what allows the accretion disk to exist at all. Angular momentum needs to be transported outward to let matter fall inward, and magnetic fields provide a mechanism for this transport. Tangled field lines connect different parts of the disk, and as they wind, up and snap, they transfer momentum and energy. Some theoretical models suggest that the magnetic field might even be what launches the jets. If the field lines thread through the black hole's event horizon and out through the disk, they could extract rotational energy from the black hole itself, the Blandford-Znajek process named after the physicists who proposed it in 1977. The spinning black hole drags the magnetic field lines around, and this rotation pumps energy into the plasma, accelerating it outward at relativistic speeds. If this is correct, then the jets are powered not just by accretion, but by the black hole's rotation. The black hole is a flywheel, storing rotational energy, and the magnetic field is the mechanism that taps into that reservoir. Eventually, over billions of years, this process would spin down the black hole, extracting its angular momentum and converting it to jet power. It's a beautiful mechanism. It's also viciously complicated, involving physics at the intersection of general relativity, plasma dynamics, and electromagnetism. We can simulate it on supercomputers now, and the simulations look promising, matching many observed properties of quasar jets. But the devil is in the details, and those details are still being worked out. Here's something that will bother you. We still don't know exactly how supermassive black holes form in the first place. The stellar mass black holes are straightforward. Massive stars collapse, their cores implode, and you get a black hole with a few dozen solar masses. Simple, well understood, no mysteries, but supermassive black holes are 1 million to 1 billion times more massive. You can't make those from a single stellar collapse, and yet we find them in the early universe, in quasars that existed less than 1 billion years after the Big Bang. That's not much time, cosmically speaking. How do you grow 1 billion solar mass black hole in that short period? If you start with a stellar mass black hole and let it accrete at the Eddington limit, the maximum sustainable rate, it would take much longer than 1 billion years to reach supermassive scales. Even accounting for the fact that the universe was denser back then, the growth timescales don't quite work. You need a head start. You need to begin with something bigger than a stellar remnant. Maybe the first black holes formed directly from the collapse of massive primordial gas clouds, creating black holes with thousands or tens of thousands of solar masses right from the start. These seed black holes could then grow through accretion and mergers to reach the supermassive scales we observe. But the conditions required for direct collapse are specific and might not have been common. Or maybe the first stars were much more massive than stars today, hundreds or thousands of solar masses, and when they collapsed, they formed intermediate mass black holes that could grow faster. Population 3 stars, the first generation born in a universe with no heavy elements, might have reached these extreme masses, or maybe supermassive black holes grow faster than the Eddington limit under certain conditions. Super Eddington accretion sounds impossible. It violates the limit by definition, but perhaps in a dense gas-rich environment with the right magnetic configuration, matter could be funneled onto a black hole faster than radiation pressure could blow it away. Some observations hint that this might happen, at least briefly. We don't know. This is an active area of research. The James Webb Space Telescope is finding quasars in the very early universe, systems that stress our formation models, and each new discovery refines our understanding but also deepens the mystery. The universe somehow found a way to create billion solar mass black holes very quickly. We're still figuring out the recipe, and I need to tell you something important here, something you need to keep in mind as we continue this journey. Everything I'm describing, the accretion disks, the jets, the magnetic fields, the feedback processes, this is our current best understanding. These are models built on decades of observations and theory, refined and tested and improved. They work. They explain most of what we see. But quasars are still teaching us. We're still finding new phenomena that challenge our models. We're still discovering quasars that don't quite fit the patterns, that push the boundaries, that force us to reconsider our assumptions. Later, in the continuation of this exploration, we're going to talk about the record breakers, the most distant quasars, the most luminous, the most massive black holes, the weirdest configurations. And some of these objects are genuinely puzzling. They're operating at extremes where our physics becomes uncertain. For now, though, I want you to sit with what we've covered. The fact that we've identified these cosmic monsters, that we understand the basic mechanism, supermassive black holes feeding on infalling matter, that we've measured their distances, their luminosities, their masses, that we've traced their light across billions of light years to telescopes on Earth, decoded their spectra, built models that match the observations. This is science at its best. Confronted with something inexplicable, we didn't give up. We didn't resort to mysticism or declare it unknowable. We built better telescopes. We developed better theories. We calculated and observed and refined our understanding until the picture came into focus. Quasars went from mysterious points of light to comprehensible physical systems. Comprehensible, but no less awe-inspiring. Understanding the mechanism doesn't diminish the wonder. If anything, it enhances it. Because now you know what you're looking at when you see a quasar in a photograph. You're seeing a black hole eating. You're witnessing the most efficient energy conversion process in the universe. You're observing light that was generated in the final moments before matter crossed the event horizon and left our reality forever. Every quasar is a monument to gravity's ultimate victory, a demonstration of what happens when matter loses its battle against space-time curvature, an engine of transformation where the ordinary becomes the extraordinary, where the slow, patient pull of gravity becomes a scream of radiation loud enough to light up the cosmos, and we've only just begun to explore them. In the next part of this journey, we'll venture further. We'll talk about the role quasars played in shaping the universe itself, how their light reionized the cosmos, how their feedback regulated galaxy formation, how they created the large-scale structure we see today. And we'll discuss the records, the brightest, the most distant, the most massive, the quasars that push against the absolute limits of what should be possible. But for now, let yourself absorb what we've covered. The discovery, the decades of confusion, the gradual understanding, the mechanism that powers these cosmic beacons. Rest now if you can. Let these ideas settle into your mind. Think about the fact that as you close your eyes tonight, there are supermassive black holes out there, billions of light years away, actively feeding, accreting matter at rates of several solar masses per year, shining with the light of trillions of suns. Their radiation is travelling through space right now, photons on journeys that will last billions of years, and some tiny fraction of those photons will eventually reach Earth, carrying information about the universe as it was when the light began its voyage. You live in a universe where such things exist, where physics permits engines of such staggering power that they make stellar fusion look primitive, where supermassive black holes lurk at the centres of galaxies, waiting for the next meal, ready to transform from dormant monsters into beacons visible across cosmic distances. Sleep well, dream of accretion disks and relativistic jets, of matter spiralling into oblivion, of the universe's most efficient engines humming in the depths of space and time. Tomorrow we'll continue. We'll talk about what these monsters have built, what they've destroyed, what records they've set. The quasars are waiting. You're awake again. Good. We have more ground to cover. Let's talk about what happens when you feed a supermassive black hole at different rates, because not all quasars are created equal. The universe has presented us with an entire spectrum of active galactic nuclei. That's the technical umbrella term. And understanding this spectrum tells us something fundamental about how black holes interact with their environments. At one end, you have the full-blown quasars we've been discussing. Brilliant, loud, feeding voraciously. At the other end, you have systems like our own Sagittarius A, nearly dormant, producing minimal emission. And in between, there's a whole taxonomy of intermediate objects, each representing a different feeding mode, a different balance of fuel supply and radiation output. Let me introduce you to the family. Seyfert galaxies were discovered in 1943 by Carl Seyfert, an American astronomer studying spiral galaxies with unusually bright cores. These cores showed strong emission lines in their spectra, signatures of hot, ionized gas moving at high velocities. For decades, Seyfert galaxies were considered a separate phenomenon from quasars, different class of objects entirely, except they're not. They're the same thing, just less luminous. Seyfert galaxies have active supermassive black holes at their centres, just like quasars. They have accretion disks, broadline regions, narrowline regions, sometimes jets. The difference is scale. Seyferts are being fed at lower rates. Their black holes are accreting matter, yes, but not at the prodigious levels that power full quasars. The result is an active nucleus that's bright enough to outshine the galaxy's central bulge, but not so bright that it drowns out the entire galaxy. When you photograph a Seyfert galaxy, you can see the spiral structure, the disk of stars, the dust lanes, and there, at the centre, a brilliant point source. The black hole is visible but not overwhelming. It's like the difference between a candle and a searchlight. Both produce light. One is manageable, the other dominates everything. Seyfert galaxies come in two flavours, Type 1 and Type 2 based on their spectra. Type 1 Seyferts show both broad emission lines and narrow emission lines. Type 2 Seyferts show only narrow lines. For years this was puzzling. Why would two otherwise similar objects have such different spectra? The answer is orientation, and this is where we need to talk about the unified model of active galactic nuclei, because it's one of the most elegant ideas in modern astrophysics. Imagine the structure around a supermassive black hole. You have the accretion disk, relatively thin, extending outward from the black hole. You have the broad line region, fast-moving clouds of gas close to the black hole, orbiting at thousands of kilometers per second. Further out, you have the narrow line region, slower-moving gas in a more extended volume. And surrounding much of this structure, you have a dusty torus. A torus is just a donut shape. A thick ring of dust and gas encircling the black hole's equatorial plane, extending from perhaps a few light years to tens of light years from the centre. This torus is opaque. It blocks our view of whatever lies behind it. Now, if we're looking at this system from an angle where we can see straight into the accretion disk and broad line region, looking down from above the torus, we see everything. We see broad emission lines from the fast-moving gas close to the black hole and narrow lines from the more distant gas. This is a Type 1 Seyfert, or a Type 1 quasar if it's sufficiently luminous. But if we're viewing the system edge-on, with the dusty torus blocking our direct view of the inner regions, we only see the narrow line region, which extends above and below the torus. We can't see the broad line region. It's hidden behind the dust. This is a Type 2 Seyfert. Same object, same physical structure, different appearance based solely on viewing angle. This unified model explains so much. It accounts for the different types of Seyferts. It predicts that if you observe a Type 2 object in polarized light, light that's been scattered, you might see broad lines reflected off dust or gas above the torus, and indeed we do. It suggests that the ratio of Type 1 to Type 2 objects should relate to the opening angle of the torus, and the statistics match. It's beautiful. It took a confusing zoo of different active galactic nucleus types and revealed they're all the same beast viewed from different angles. But wait, there's more. Radio galaxies fit into this scheme too. Radio galaxies are exactly what they sound like. Galaxies that are powerful radio sources. They were among the first active galactic nuclei discovered, picked up by early radio surveys in the 1950s. When you observe them in radio wavelengths, you see extended lobes of emission, sometimes spanning millions of light years, connected to the central galaxy by jets. These jets are the relativistic beams we talked about earlier, launched from near the black hole and ploughing through the intergalactic medium. Where the jets terminate, they create shock waves, energizing the surrounding gas and producing massive lobes of synchrotron emission. Some radio galaxies have lobes so large they dwarf the host galaxy itself. We're talking about structures that take light hundreds of thousands of years to cross, powered by a central engine smaller than our solar system. Radio galaxies come in two types as well, Phaneroff-Rayleigh Type 1 and Type 2, named after the astronomers who classified them in 1974. FRI galaxies have jets that brighten toward the centre. FR2 galaxies have jets that brighten toward the edges, terminating in bright hotspots where the jet impacts the intergalactic medium. The difference relates to jet power and the density of the surrounding environment, but both types are fundamentally the same phenomenon, supermassive black holes launching jets. And here's where orientation matters again. If you're looking at a radio galaxy from the side, you see the jets extending perpendicular to your line of sight. You see the lobes. You can measure the structure. But if you're looking straight down one of the jets, if the jet is pointed almost directly at you, the appearance changes dramatically. Relativistic beaming comes into play. When a source is moving toward you at close to the speed of the light, its emission is concentrated in a narrow cone in the forward direction. The light is Doppler shifted to higher energies and the brightness is amplified by a factor that depends on the jet's speed and viewing angle. If you're in the beam, the jet appears vastly brighter than it would from the side. A radio galaxy viewed down the jet becomes a blazar. The same object, different orientation, and blazars are wild. Their brightness varies rapidly, sometimes doubling or halving in hours. Their spectra show strong Doppler-boosted emission. They're among the brightest objects in the gamma-ray sky, because the relativistic particles in the jet are producing high-energy photons through inverse Compton scattering and other processes. Add it all together, and the unified model gives us a complete picture. Quasars, Seyfert galaxies, radio galaxies, blazars, they're all supermassive black holes with accretion disks, sometimes with jets, viewed from different angles and at different levels of activity. The diversity we observe in active galactic nuclei isn't because there are fundamentally different types of objects. It's because we're seeing the same types of objects from different perspectives and in different feeding states. This is a triumph of astrophysics. We've decoded the puzzle, we understand the architecture, but understanding the structure doesn't tell us everything. We still need to understand the dynamics. How does matter actually get from the outer regions of a galaxy down to the black hole? How do accretion disks form and maintain themselves? How are jets launched and collimated? Let's start with the accretion problem. You might think it's simple. Gravity pulls matter inward, matter falls into the black hole, done. But it's not that simple. Matter in the galaxy has angular momentum. It's orbiting the galactic centre. An orbital angular momentum prevents it from falling straight in. If you want matter to accrete onto the black hole, you need to remove that angular momentum somehow. In the accretion disk itself, this happens through viscosity. The inner parts of the disk orbit faster than the outer parts, that's just Kepler's laws, and this differential rotation creates shear. Friction between adjacent layers of the disk transfers angular momentum outward and allows matter to spiral inward. The friction also heats the disk, producing the thermal emission we observe. But viscosity in a thin gas disk shouldn't be strong enough to produce the accretion rates we observe. Normal molecular viscosity is far too weak. For decades, this was a problem. The disks shouldn't work according to basic fluid dynamics. The solution is turbulence. The disks aren't smooth laminar flows. They're chaotic, turbulent, with eddies and instabilities churning the gas. This turbulence provides an effective viscosity much higher than molecular viscosity. But what drives the turbulence? Magnetic fields. Again, magnetic fields. There's an instability called the magnetorotational instability, or MRI, that operates in ionized magnetized disks. Small perturbations in the magnetic field couple to the differential rotation, and these perturbations grow exponentially, creating turbulence. The MRI is incredibly efficient at generating the turbulence needed to transport angular momentum. It's probably the fundamental mechanism that allows accretion disks to exist. We've confirmed this through simulations. Magnetohydrodynamic codes running on supercomputers can model accretion disks, including the MRI, and the results match observations. The disks they produce have the right temperatures, the right densities, the right accretion rates. The physics works. But getting matter from the galaxy at large down to the accretion disk scale, that's a different problem. The accretion disk might only extend to a few light years from the black hole. How does matter get there from the galactic disk, which is tens of thousands of light years across? This is where large-scale processes come in. Galaxy mergers, as I mentioned, are one mechanism. The gravitational interaction during a merger can funnel gas toward the centre. But mergers are discrete events, and quasars can remain active for millions of years. There must be other mechanisms that can sustain the fuel supply. Bars can do it. Many galaxies have bar-shaped distributions of stars in their central regions. These bars create non-axis symmetric gravitational potentials that can torque gas clouds, removing angular momentum and driving inflows. Gas spirals along the bar, falls inward, and accumulates near the galactic centre, where it can eventually feed the black hole. Spiral density waves can help too. The spiral arms in a galaxy aren't fixed structures. They're density waves, regions where stars and gas bunch up temporarily as they orbit. These waves can compress gas, trigger instabilities, and drive inflows on smaller scales. And sometimes it's just stochastic. Random encounters between gas clouds, minor perturbations from passing dwarf galaxies, cumulative effects of stellar winds and supernovae, all these can occasionally conspire to send a large mass of gas toward the central black hole. The quasar lights up, burns through the fuel supply over a few million years, then fades. The cycle repeats when the next batch of fuel arrives. The point is, feeding a supermassive black hole requires coordination across enormous ranges of scale. You need mechanisms operating at kiloparsec scales to funnel gas inward, mechanisms at parsec scales to form and maintain the accretion disk, and mechanisms at subparsec scales to actually deliver matter to the black hole. It's a multi-scale problem, and we're still working out all the details. Now, let's talk about what happens to the energy. A quasar converting mass to energy at 10% efficiency, accreting several solar masses per year. That's an energy output of roughly 10 to the 47th ergs per second. Let me put that in perspective. The Sun's luminosity is about 4 times 10 to the 33rd ergs per second. A quasar is 10 trillion times more luminous than the Sun. That energy has to go somewhere. It radiates outward as photons across the electromagnetic spectrum. It drives winds and outflows. It powers jets. And all of this energy interacts with the surrounding environment. Close to the black hole, within the inner few light years, the radiation field is so intense it ionizes everything. Any molecules are torn apart. Any atoms are stripped of their electrons. You're left with a plasma of bare nuclei and free electrons, all heated to millions of degrees. This is not an environment conducive to chemistry, or complexity, or life. This is a region where only the most fundamental physics applies. Further out, in the host galaxy, the quasar's energy drives large-scale winds. Gas accelerated to thousands of kilometers per second streams outward from the nucleus, sweeping through the galaxy. These winds carry energy and momentum, and when they collide with the galaxy's interstellar medium, they create shocks. The shocks heat the gas, compress it, sometimes trigger star formation, sometimes suppress it. This is quasar feedback in action. The black hole is regulating its environment. By driving winds, it's removing the gas that would otherwise form stars or feed the black hole itself. It's a self-limiting process. The more powerfully the quasar shines, the more effectively it clears out its surroundings, cutting off its own fuel supply. Observationally, we see evidence of this feedback everywhere. We see galaxies with massive molecular outflows, gas being ejected at rates comparable to the star formation rate. We see galaxies where star formation has been quenched, shut down, likely by energy input from the central black hole. We see correlations between black hole mass and the properties of the host galaxy's bulge, suggesting a deep connection between black hole growth and galaxy evolution. This connection is profound. It suggests that supermassive black holes aren't just passengers in galaxies. They're active participants in galactic evolution. They shape the galaxies that host them. There's a relationship called the M-sigma relation. M is the black hole mass. Sigma is the velocity dispersion of stars in the galaxy's bulge, a measure of how fast the stars are moving, which relates to the bulge's mass. Plot black hole mass against sigma for many galaxies, and you get a tight correlation. More massive bulges have more massive black holes in a very specific ratio. Why? The black hole is a tiny fraction of the galaxy's mass, typically about 1,000th the mass of the bulge. How does the black hole know about the properties of the bulge? How did this relationship emerge? The answer is probably feedback. As the galaxy forms and the black hole grows through accretion, the energy released regulates the growth of both. The black hole accretes until its feedback becomes strong enough to shut off infall. The galaxy forms stars until quasar-driven. Winds expel the gas. The two processes are coupled. They co-evolve. The result is the tight correlation we observe. This is still an active area of research. The details are complicated, involving simulations that track galaxy formation, black hole growth, star formation, and feedback processes across cosmic time. But the broad picture seems clear. You can't understand galaxies without understanding their central black holes, and you can't understand supermassive black holes without understanding the galaxies they inhabit. Quasars are not isolated phenomena. They're intimately connected to the cosmic web, to the formation of structure in the universe, to the cycles of matter and energy that shape everything we see. And speaking of the cosmic web, let me tell you what quasars have done for cosmology. Quasars are bright, insanely bright. That means we can see them at enormous distances. The most distant quasars we've found have redshifts greater than 7, meaning their light has been stretched by a factor of 8 as the universe expanded during the photon's journey to us. These quasars existed less than 1 billion years after the Big Bang. They're showing us the universe in its infancy, and their light has passed through everything between them and us. As quasar light travels across cosmic distances, it passes through clouds of gas in the intergalactic medium. These clouds absorb specific wavelengths of light, creating absorption lines in the quasar's spectrum. Each cloud imprints its signature, and by analysing these absorption features, we can map the distribution of gas along the line of sight. This is called the Lyman alpha forest. It's a series of absorption lines created by neutral hydrogen in the intergalactic medium, and it looks like a forest of lines in the quasar spectrum. Each line corresponds to a cloud at a specific redshift, a specific distance and cosmic epoch. The Lyman alpha forest is a goldmine of information. It tells us about the density and temperature of the intergalactic medium. It reveals the large-scale structure of the universe, the filaments and voids that make up the cosmic web. It provides constraints on cosmological parameters and the formation of structure. Without quasars, we wouldn't have this tool. We need bright background sources to backlight the intergalactic medium, and quasars are the only objects bright enough and numerous enough to do the job. Quasars have also been used as standard rulers and probes of cosmic expansion. By studying the clustering of quasars and correlating their positions with other large-scale structures, cosmologists can measure the expansion history of the universe. Quasars contribute to our understanding of dark energy, the mysterious component driving the accelerated expansion we observe today. They're laboratories for extreme physics. The environments near quasar black holes involve strong gravity, high magnetic fields, relativistic speeds, intense radiation, fields, conditions we can't reproduce in any terrestrial lab. By studying quasars, we test general relativity in the strong field regime. We probe how matter behaves under extreme conditions. We observe physics at energy scales inaccessible to particle accelerators. Some quasars show evidence of binary supermassive black holes. Two black holes, each millions to billions of solar masses, orbiting each other at the center of a merged galaxy. These systems are rare, but we've found candidates. And they're interesting because when supermassive black holes merge, they produce gravitational waves, ripples in space-time that carry energy away from the system. We haven't detected gravitational waves from supermassive black hole mergers yet. The frequencies are too low for current detectors like LIGO, which are designed to detect waves from stellar mass black holes. But future detectors, space-based interferometers like LISA, the Laser Interferometer Space Antenna, will be sensitive to these lower frequencies. When LISA flies, probably in the 2030s, it should detect gravitational waves from merging supermassive black holes, and some of those mergers will involve quasar-like systems, objects we can also observe electromagnetically, multi-messenger astronomy. Observing the same event in both gravitational waves and light, it's going to revolutionize our understanding of black hole mergers and the environments surrounding them, but that's the future. Let me bring us back to the present and wrap up this section of our journey. We've covered the discovery of quasars, the decades of confusion and gradual understanding, the mechanism, supermassive black holes accreting matter through turbulent, magnetized disks, the diversity of active galactic nuclei and the unified model that explains it, the problem of fueling black holes and the multi-scale processes involved, the energy output and its effects on the surrounding galaxy, the connections to galaxy evolution and cosmology. You should have a picture now of what quasars are and how they work. They're not isolated curiosities, they're key players in the cosmic drama. They regulate galaxy formation, they shape the intergalactic medium, they provide tools for probing the universe's structure and history, and they exist because supermassive black holes exist, and because galaxies sometimes provide these black holes with fuel. The combination creates the brightest persistent light sources in the universe. In the final part of this first exploration, the fourth segment we'll cover shortly, I'm going to delve deeper into some specific aspects: the physics of the jets, the timescales of variability, the effects of relativistic motion on our observations, the practical challenges of studying objects billions of light years away, and I'll set the stage for what's coming next: the records, the extremes, the quasars that push our understanding to its limits. But we've covered a lot. Your mind is probably saturated with information about accretion disks and feedback and magnetic fields. Let it process. Let the concepts settle. Think about the fact that right now, across the observable universe, there are thousands of supermassive black holes actively feeding. Some are just beginning their meals, their brightness ramping up as fresh gas falls inward. Others are in the middle of long feasts, sustaining luminosities that would take a galaxy of stars to match. Still others are in their final stages, the fuel running out, the brightness fading, the galaxy returning to quiescence. And all of this, the feeding, the shining, the shaping of galaxies, is happening in a universe that's fundamentally indifferent to it. The black holes aren't trying to accomplish anything. They're not aware. They're just doing what black holes do when you give them matter, accreting, radiating, existing as geometric features of space-time. Yet the consequences are profound. Quasars helped ionize the universe. They regulate star formation in massive galaxies. They contribute to the creation of the cosmic structures we inhabit. Without quasars, without supermassive black holes and their feeding cycles, the universe would look different. Galaxies would evolve differently. The cosmic web would have a different character. You exist in a universe shaped by black holes, by gravity's ultimate expression, by the most efficient engines ever devised by the laws of physics. Sleep on that. You're still here, still thinking about supermassive black holes and the galaxies they inhabit. Good. We're going to go deeper now. We're going to talk about the aspects of quasar physics that really test our understanding, the places where observation meets theory and the match isn't quite perfect, the phenomena that still generate debate in conference rooms and academic papers. Let's start with the jets, because jets are genuinely strange. I've mentioned them several times already. Relativistic. Beams of particles launch from near the black hole, extending for hundreds of thousands or even millions of light years. But I haven't really explained how bizarre they are from a physics perspective. First, there's the collimation problem. When you launch material from a region near a black hole, you might expect it to spray out in all directions, or at least in a broad cone. Instead, jets remain tightly focused over enormous distances. They're narrow, sometimes only a few light years wide, and they stay narrow even as they travel across intergalactic space. How? Magnetic fields are part of the answer. If the jet is threaded with magnetic field lines, and if these field lines are helical, twisted around the jet's axis, they can provide a kind of magnetic confinement. The field lines create pressure that squeezes the jet, keeping it collimated. It's like wrapping the jet in an invisible magnetic sleeve. But maintaining this collimation over millions of light years requires very specific field configurations. The fields need to be strong enough to confine the flow, but not so strong they disrupt it. They need to maintain their structure despite turbulence and instabilities. And the jet needs to be carrying enough energy in the magnetic field, we say it needs to be magnetically dominated, for this confinement to work. Simulations show it can happen. We can create numerical jets that stay collimated over long distances if we set up the initial conditions correctly. But translating from simulation to reality is always tricky. Nature has to arrange the right conditions without the benefit of a theorist tweaking parameters. Then there's the particle acceleration problem. The particles in jets, mostly electrons and protons, are moving at Lorentz factors of 10 to 100 or more. That means they're travelling at 99.99% of the speed of light, or faster. How did they get accelerated to these speeds? Magnetic reconnection might be involved. When magnetic field lines with opposite orientations come together, they can reconnect, releasing energy. This energy goes into accelerating nearby particles. Reconnection is efficient and can produce the kinds of particle energies we observe in jets. Shock acceleration is another mechanism. As the jet ploughs through the ambient medium, it creates shock waves. Particles crossing back and forth across the shock front can gain energy with each crossing, building up to relativistic speeds through a process called Fermi acceleration. Both mechanisms probably operate. Jets are complicated structures with turbulence, shocks, reconnection events, and who knows what else happening simultaneously. The particles we detect, the ones producing the synchrotron radiation and gamma rays we observe, are likely the product of multiple acceleration episodes. And here's something that bothered physicists for years. The jets are too bright. Let me explain. When you calculate how much energy you need to produce, the observed synchrotron emission from a jet, and you assume a reasonable magnetic field strength, you get a number, call it E. But when you calculate the energy required to explain the inverse Compton emission, the high energy photons produced when relativistic electrons scatter low energy photons, you get a different number, often much larger. This is called the Compton catastrophe. The two processes should be related in a predictable way, but the observations don't match the predictions. Either our estimates of the magnetic field are wrong, or there's something about the particle distribution we don't understand, or the jets aren't as simple as our models assume. Recent work suggests the jets might have complex internal structures. Maybe there's a fast inner spine surrounded by a slower outer layer. Maybe the magnetic field strength varies significantly across the jet. Maybe the particle acceleration is happening in localized regions, not uniformly throughout the jet volume. We're still figuring it out. Every new observation adds detail, but it also adds complexity. Now let's talk about time, specifically timescales, because quasars vary, and the timescales of variation tell us about the physical scales involved. I mentioned earlier that quasars can vary on timescales from hours to years, but let's dig into what this means. If a quasar brightens over the course of a day, that variation must originate from a region small enough that light can cross it in a day. Otherwise, different parts of the region would be varying at different times, and the overall variation would be smeared out. This is the light-crossing time argument, and it's fundamental to interpreting variability. One light day is about 26 billion kilometers. For comparison, Neptune's orbit is about 9 billion kilometers across. So when we observe day-scale variations, we're probing regions smaller than our solar system. Regions that are producing luminosities comparable to entire galaxies. Some quasars show even faster variations, flickering on our timescales or even minutes. This pushes the emitting region down to sizes comparable to the event horizon of the supermassive black hole itself. We're seeing variations from the innermost parts of the accretion disk, the regions where relativistic effects are strongest, where the orbital velocities approach the speed of light. These rapid variations are a window into the strong gravity regime. They let us test general relativity's predictions about how matter behaves near event horizons. Some of the variations might come from hotspots in the accretion disk, clumps of material orbiting the black hole and producing enhanced emission, as they whip around at relativistic speeds. If you could time resolve these hotspots, you'd see periodic variations, the hotspot orbiting, brightening and dimming as it moves toward and away from us, Doppler shifted and time dilated by its extreme motion. We've observed some quasars that show quasi-periodic oscillations, variations that repeat with a characteristic timescale. These might be hotspots, though proving it requires careful modelling. On longer timescales, months to years, the variations probably reflect changes in the accretion rate. The disk isn't feeding the black hole at a perfectly steady rate. There are fluctuations. Perhaps a denser clump of material spirals in, increasing the accretion rate and brightening the quasar. Perhaps an instability in the disk temporarily disrupts the flow, decreasing the brightness. These variations propagate through the disk on viscous timescales, which can be months or years depending on the disk's structure. And on the longest timescales, thousands to millions of years, quasars turn on and off entirely. A galaxy goes from having a dormant black hole to hosting an active quasar as a new supply of fuel arrives. The quasar shines for a few million years, then fades as the fuel is exhausted. The black hole returns to dormancy, waiting for the next meal. This duty cycle, the fraction of time a supermassive black hole spends in an active state, is important for understanding quasar demographics. If we observe a certain number of quasars at any given time, and we know the duty cycle, we can estimate how many galaxies have gone through a quasar phase in their past. The answer is most of them. Probably every massive galaxy has hosted a quasar at some point. The supermassive black holes are ubiquitous, and most galaxies have gone through merger events or other processes that could trigger accretion. Your own galaxy, the Milky Way, likely had a quasar phase billions of years ago. Maybe multiple phases. It's a strange thought. Looking up at the night sky, the stars of the Milky Way arrayed around you, and knowing that billions of years ago the galactic center was a brilliant beacon, outshining all those stars combined. Life on Earth, of course, didn't exist then, the sun didn't exist, but if sun had, and if Earth had been in position to observe, the night sky would have been dominated by a single brilliant point of light in the direction of Sagittarius. A quasar. Our quasar. Now let's address something practical. How do we actually study objects that are billions of light years away? Observational astronomy at these distances is challenging in ways the public doesn't always appreciate. You're collecting photons that have been travelling for eons, redshifted by the universe's expansion, diluted by distance until the signal is almost lost in the noise, and you're trying to extract meaningful information from that faint signal. Start with spectroscopy. Taking a spectrum of a quasar means spreading out its light by wavelength and measuring the intensity at each wavelength. This gives you the emission and absorption lines we've been discussing. But quasars are point sources, they don't have angular size on the sky, so you're working with very little light. Large telescopes help. The bigger the mirror, the more photons you collect. The Keck telescopes in Hawaii have 10-meter mirrors. The European Extremely Large Telescope, currently under construction, will have a 39-meter mirror. More collecting area means you can observe fainter objects or take higher resolution spectra. But even with large telescopes, you're often exposing for hours to get a decent spectrum of a distant quasar. Photons are arriving at a trickle. You're counting individual photons, measuring their energies, building up a spectrum bit by bit. It's patient work. Redshift complicates things. A quasar at redshift 6 is emitting most of its light in the ultraviolet, but by the time that light reaches us, it's been stretched into the optical and infrared. To observe the quasar's intrinsic ultraviolet emission, you need to point your telescope's infrared detectors at it. You need detectors sensitive to the right wavelengths, and you need to account for Earth's atmosphere, which absorbs strongly in some infrared bands. This is why space telescopes are valuable. Hubble, operating above the atmosphere, can observe ultraviolet light that never makes it to the ground. The James Webb Space Telescope, optimized for infrared, can observe the redshifted light from the most distant quasars, the ones at redshift 10 or higher, existing just a few 100 million years after the Big Bang. And speaking of JWST, it's revolutionizing quasar studies. It's finding quasars in the very early universe, objects that shouldn't quite exist according to our formation models, because there hasn't been enough time to grow such massive black holes. Each discovery is a puzzle piece, a constraint on our theories. Time domain astronomy adds another dimension. Instead of just taking a single spectrum and moving on, you observe the same quasar repeatedly over months or years, tracking how it changes. This reveals variability patterns, helps identify periodic oscillations and constraints, the physical processes driving the variations. Some surveys are doing this systematically. The Zwicky Transient Facility, for example, scans the sky repeatedly, building up light curves for thousands of quasars. The Vera Rubin Observatory, when it comes online, will do this on an even larger scale, observing billions of objects and tracking their variations. Multi-wavelength observations are crucial. Quasars emit across the entire electromagnetic spectrum, and each wavelength range probes different physics. Radio observations reveal the jets and lobes. Infrared observations probe the dusty torus and cooler regions. Optical observations show the accretion disk and broadline region. X-rays come from the hot inner disk and corona. Gamma rays trace the most energetic processes in the jets. By observing a quasar at multiple wavelengths simultaneously, you build a complete picture. You see how the different components are connected, how variations in one wavelength correlate with variations in another. It's like observing a symphony from multiple positions in the concert hall. Each vantage point gives you different information about the performance. Interferometry extends our capabilities. Instead of using a single telescope, you combine the signals from multiple telescopes, creating an effective aperture as large as the distance between them. The Event Horizon Telescope, which famously imaged the black hole in M87, is an interferometer spanning the Earth. It has an effective resolution of about 20 microarc seconds, small enough to resolve structure near the event horizons of the nearest supermassive black holes. We haven't imaged a quasar with EHT level resolution yet. Quasars are too distant. But future interferometers, perhaps operating in space, might achieve the resolution needed to image quasar accretion disks directly. Imagine seeing the structure of the disk, the hot spots, maybe even the base of the jets. It would be transformative. All of this, the telescopes, the detectors, the interferometers, the analysis techniques, represents a century of technological and theoretical development. We've gone from barely detecting quasars as mysterious points of light to studying their detailed physics, their variability, their spectra across the electromagnetic spectrum. And we're not done. Every new instrument opens new windows. Every new survey finds new objects. The rate of discovery is accelerating. Which brings me to what's coming next. In this first part of our quasar exploration, we've covered the fundamentals, the history, the mechanism, the physics. You understand what quasars are now. You know they're supermassive black holes feeding on infalling matter. You know about accretion disks and jets and feedback. You know how they connect to galaxy evolution and cosmology. But we haven't yet talked about the extremes, the records, the most distant quasars, showing us the universe in its infancy, the most luminous, shining with the light of 10,000 galaxies, the most massive black holes, billions of times heavier than our sun, the strangest configurations, the objects that challenge our models, the outliers that force us to reconsider our assumptions. That's what's coming in the next part of this journey. The records, the cosmic champions, the quasars that define the edges of what's possible. We'll discuss how quasars helped reionize the universe, transforming it from a neutral fog into the transparent medium we see today. We'll talk about their role in shaping the large-scale structure, the cosmic web of filaments and voids. We'll explore how they regulate the most massive galaxies, preventing them from forming too many stars. And we'll introduce you to specific objects, quasars with names and coordinates, the brightest ever observed, the most distant ever confirmed, the ones with the fastest growing black holes, the ones with the most powerful jets, the ones that broke records and redefined our understanding. Some of these objects are genuinely puzzling. They exist at times and places where our models say they shouldn't. They're brighter than they should be, more massive than we can explain, feeding faster than physics should allow. They're anomalies, and anomalies are where breakthroughs happen. But that's for next time. For now, let's consolidate what we've learned. Quasars are real. They're not exotic physics or unexplained phenomena. They're supermassive black holes with accretion disks, governed by the same laws of physics that apply everywhere in the universe. We understand the basic mechanism. We can calculate the luminosities, the temperatures, the spectra. We can model the disks and jets with reasonable accuracy. But the details are rich and complex. The physics involves general relativity, magnetohydrodynamics, plasma physics, radiative transfer, particle acceleration. The observations require cutting-edge telescopes and detectors. The interpretation requires careful analysis and modelling. Quasars are testaments to what the universe can create when you take gravity seriously, when you let matter compress under its own weight until space-time itself is warped beyond recognition. When you feed that compressed mass with fresh matter and convert the infall energy into radiation, the efficiency is staggering. 10% mass-to-energy conversion. Nothing else in nature comes close. Nuclear fusion maxes out at less than 1%. Chemical reactions are a fraction of a percent. But black hole accretion reaches 10%. It's the most efficient engine permitted by physics, and quasars are running those engines at maximum throttle. They're also finite. Every quasar will eventually fade, the fuel supply will run out, or feedback will blow away the remaining gas, or the galaxy will exhaust its ability to funnel matter to the centre. The black hole will remain, massive and patient, but dormant. The light show will end. In the far future, when star formation has ceased across the universe, when the last stars have burned out and the galaxies are dark, the supermassive black holes will still be there, cold, invisible, waiting in the centres of dead galaxies, monuments to the era when the universe was bright and active and galaxies were being born. But that future is trillions of years away. For now, the universe is still alive. Stars are still forming, galaxies are still merging, black holes are still being fed, and quasars are still shining. As you rest, as you let these ideas settle into your mind, think about the photons. Right now, at this moment, there are photons from distant quasars streaming through the space you occupy. Most pass through you harmlessly, your mostly empty space at the atomic level. But some are absorbed by the detectors of telescopes scattered across Earth's surface and in orbit above. Each photon is a messenger. It carries information about the quasar that emitted it, encoded in its energy and polarization. It travelled across cosmic distances, through expanding space, navigating the universe's large-scale structure. And it arrived here, now to be detected and analysed and added to our growing understanding. Some of those photons were emitted before the Earth formed, before the Sun ignited, before the gas cloud that would become our solar system had begun to collapse. They've been travelling for so long that entire stellar lineages have come and gone during their journey, and yet they're still coherent, still carrying their information, still capable of telling us about the distant past. That's the power of light. The universe is transparent to it, at least to most wavelengths, and light travels at the absolute speed limit of causality. Nothing in the universe can carry a signal faster. Light is how the cosmos communicates across distance and time. Quasars speak to us in this language. They're beacons in the deep past, transmitting information about conditions we can't directly access. And we've learnt to listen. We've built the instruments and developed the theories to decode their messages. It's a remarkable achievement. You live in an era when we can study the universe's history across 13 billion years, when we can observe objects so distant their light is older than most stars, when we can probe the physics of black holes and accretion and relativistic jets. None of this was possible a century ago. We didn't know galaxies existed beyond the Milky Way. We had no idea the universe was expanding. Black holes were speculation. Quasars were undreamed of. Now we've mapped them, catalogued thousands, studied their spectra and variability and structure, built models that explain their behaviour, connected them to the broader picture of cosmic evolution, and we're not stopping. The next generation of telescopes will go deeper, see farther, resolve finer details. We'll find quasars in even earlier epochs. We'll track their evolution with unprecedented precision. We'll test our models against better data. The field is alive, growing. Every year brings new discoveries. Rest now. Let your mind absorb what we've covered. The journey from discovery to understanding, the physics of accretion and jets, the connection to galaxy evolution, the observational challenges and how we've overcome them. When you're ready, when you've processed this foundation, we'll continue. We'll talk about the records, the extremes, the quasars that rewrote the textbooks. The brightest objects in the universe are waiting to share their secrets. And we're just getting started. You're back. You've rested, processed, thought about supermassive black holes and their feeding patterns. But we're not quite done with the fundamentals. There are more layers to peel back, more aspects of quasar physics that need examination. Before we move on to the records and extremes, let me tell you about something called reverberation mapping, because it's one of the cleverest techniques we've developed for studying quasar structure. The problem is simple to state. We can't spatially resolve quasars. Even the nearest ones are too distant. Their accretion disks, broadline regions, all the interesting structures are too small to see directly, even with our best telescopes. It's like trying to study the anatomy of a cell with your naked eye. You need magnification, but there's no lens powerful enough to magnify something billions of light years away. So we use time instead of space. Here's how it works. The continuum emission, the smooth background light from the accretion disk, varies. We've established that. These variations are intrinsic to the disk. caused by changes in the accretion rate or instabilities in the flow. Now, this varying continuum illuminates the broadline region, the fast-moving clouds of gas orbiting the black hole. The clouds absorb some of the continuum, photons, and re-emit them as emission lines. But here's the key. The emission lines respond to changes in the continuum with a time delay. If the continuum brightens, the emission lines brighten too, but not instantly. There's a lag, a light travel time delay, corresponding to how long it takes light to travel from the accretion disk to the broadline region. Measure that lag, and you've measured the distance between the disk and the broadline region. Measure how the lag varies for different emission lines, and you've mapped the structure of the broadline region itself. This is reverberation mapping. You're using time delays to reconstruct spatial structure. It's elegant. It's also painstaking. You need long-term monitoring campaigns, observing the same quasar night after night for months or years, building up detailed light curves for both the continuum and the emission lines. You need good time resolution and signal to noise. You need patience, but it works. We've measured broadline region sizes for dozens of quasars using this technique. The typical distance is a few light days to a few light months from the central black hole, depending on the black hole's mass and luminosity. More luminous quasars have larger broadline regions, which makes sense. Stronger radiation pushes the clouds farther out. And here's the bonus. Once you know the size of the broadline region, you can measure the black hole's mass. The clouds in the broadline region are orbiting the black hole. Their velocities are encoded in the width of the emission lines, the Doppler broadening we observe. If you know the orbital velocity and the orbital radius, you can calculate the mass being orbited. Basic Kepler. This is how we've measured black hole masses for thousands of quasars, not through direct observation of orbiting stars, as we can do for Sagittarius A in our own galaxy, but through reverberation mapping and spectroscopy. It's indirect, but it's robust. The masses we get are consistent with other independent measurements when those are available. The masses range from millions to billions of solar masses. The typical quasar black hole is around 1 billion solar masses, give or take an order of magnitude. The smallest we've found in quasars are about 10 million solar masses, smaller than that, and the object isn't luminous enough to qualify as a quasar. The largest exceed 10 billion solar masses, approaching what seems to be a theoretical maximum for how massive a black hole can grow. And yes, there appears to be a maximum. Not a hard limit imposed by physics, but a practical one imposed by the realities of galaxy formation and evolution. Remember the Eddington limit. At a given black hole mass, there's a maximum luminosity the system can sustain. This corresponds to a maximum accretion rate. You can't feed the black hole faster than the Eddington rate over long periods without the radiation blowing away the infalling matter. If a black hole is accreting at the Eddington rate continuously, it grows exponentially. The E-folding time, the time it takes to increase its mass by a factor of E, about 2.7, is approximately 45 million years for standard accretion disk physics. Start with a 100 solar mass seed black hole, let it accrete at the Eddington rate, and after 1 billion years you'd have a black hole of several billion solar masses. That works, barely, for explaining the massive black holes we observe in quasars from the early universe. But it requires continuous Eddington rate accretion for 1 billion years. No interruptions, no periods of starvation, perfect conditions for feeding. That's optimistic. Real quasars don't accrete continuously at maximum rates. They have duty cycles. They turn on and off as fuel becomes available or runs out. The average accretion rate over a black hole's lifetime is probably much lower than the Eddington rate. Moreover, as black holes grow more massive, they become more effective at shutting off their own fuel supply through feedback. A 10 billion solar mass black hole shining at the Eddington limit is so luminous that its radiation pressure can evacuate gas from an entire galaxy. It creates winds powerful enough to unbind the galaxy's gas reservoir. At that point, the black hole has effectively capped its own growth. This might explain why we don't see black holes much more massive than 10 to 20 billion solar masses, They hit a self-regulation limit. They grow until their feedback becomes so powerful that further growth is suppressed. The galaxy and black hole reach an equilibrium state. But we're finding objects that challenge even this picture. Quasars in the very early universe with black holes that seem too massive for the available time. Objects that require either super Eddington accretion or much more massive seed black holes than our models predict. We'll talk about these outliers in the next part of our exploration. For now, just know that the universe keeps surprising us. Let me shift gears and talk about dust, because dust plays a crucial role in quasar physics that often gets overlooked. The dusty torus I mentioned earlier, the donut-shaped structure encircling the black hole at distances of a few light years, isn't just a geometric curiosity. It's an active participant in the energy budget. The torus absorbs ultraviolet and optical radiation from the accretion disk and re-radiates that energy in the infrared. This makes quasars bright infrared sources. In fact, some of the most luminous infrared sources in the universe are dust-enshrouded quasars. The dust is being heated to hundreds of degrees Kelvin by the quasar's radiation, and at those temperatures it glows brightly in the mid to far infrared. From an observational standpoint, this infrared emission is useful. It's less affected by dust extinction along our line of sight compared to optical light. If a quasar is embedded in a dusty galaxy, its optical light might be heavily absorbed, making it appear much fainter. But the infrared light penetrates the dust more easily. By observing in the infrared, we can find quasars that would be missed in optical surveys. The James Webb Space Telescope is particularly good at this. Its infrared sensitivity and resolution allow it to detect dust-obscured quasars that were invisible or barely visible to previous telescopes. Some of the quasars JWST is finding are so heavily enshrouded in dust that they were completely unknown before. This matters for demographics. If a significant fraction of quasars are hidden behind dust, then optical surveys have been missing them. The total population of quasars might be larger than we thought. The fraction of black holes in active states might be higher. Our understanding of how often supermassive black holes accrete needs updating. Dust also affects the spectral energy distribution, the SEDI of quasars. The SEDI is a plot of luminosity versus wavelength across the entire electromagnetic spectrum. For a quasar, the SED typically has multiple components. There's the ultraviolet and optical emission from the accretion disk, often modelled as a thermal spectrum with a characteristic temperature. There's the infrared emission from the heated dust. There's the X-ray emission from the hot corona above the disk. If jets are present, there's additional emission from synchrotron radiation and inverse Compton scattering. By fitting models to the observed SED, we can decompose the different components and learn about the physical structure. How hot is the accretion disk? How much mass is in the dusty torus? What's the covering factor, the fraction of the sky, as seen from the black hole, that's obscured by dust? Is there a corona? And if so, what's its temperature and optical depth? This kind of detailed SED modelling requires multi-wavelength observations. You need data from radio to gamma ray spanning 10 orders of magnitude in photon energy. No single telescope can cover that range, so you combine observations from multiple instruments. Radio arrays for the long wavelengths, infrared space telescopes for the dust emission, optical and UV for the disk, X-ray satellites for the hot corona and any inverse Compton emission. Coordinated multi-wavelength campaigns are logistically complex. Different telescopes have different observing schedules. Some are oversubscribed and difficult to get time on. Coordinating simultaneous observations requires planning months or years in advance, but the payoff is worth it. A complete SED gives you a comprehensive picture of the quasar's physical state. Now let me tell you about microlensing, because it's another technique that's revealed unexpected details about quasar structure. Gravitational lensing, as I mentioned earlier, occurs when a massive object lies between us and a distant quasar. The intervening mass bends the quasar's light, creating multiple images. But lensing isn't just a curiosity, it's a tool. In some lensed quasar systems, individual stars in the lensing galaxy act as additional microlenses. As these stars move in their orbits, they pass across the different images of the lensed quasar, causing brief magnification events. The quasar brightens temporarily as a star crosses the line of sight, then dims again as the alignment changes. These microlensing events are sensitive to the structure of the quasar on very small scales much smaller than we can resolve directly. By studying how the brightness changes during a microlensing event, we can infer the size of the emitting region. Here's the key insight. If the emitting region is smaller than the Einstein radius of the microlensing star, the magnification is strong and highly variable. If the emitting region is larger, the magnification is weaker and smarter out over time. By measuring the timescale and amplitude of microlensing variations, we can estimate the size of the quasar's accretion disk. The results have been surprising. Accretion disks appear to be larger than theoretical models predict. The standard thin disk models, based on assumptions about viscosity and energy transport, predict disks of a certain size for a given black hole mass and accretion rate. But microlensing observations consistently find disks that are several times larger. Why? We're not entirely sure. Maybe the disks are puffed up by magnetic pressure, making them thicker and more extended than the simple models assume. Maybe there's additional emission from an outflowing wind or corona that contributes to the observed size. Maybe the viscosity prescription we use in the models is wrong. This is an active area of research. The discrepancy between theory and observation is significant enough that it demands explanation. Either our models are missing important physics, or our interpretation of the microlensing data needs refinement. Probably both. Let me talk about something that might seem esoteric but is actually fundamental: the corona. Above the accretion disk, there's a region of extremely hot diffuse plasma called the corona. Temperatures here reach tens of millions to hundreds of millions of degrees. This corona is the source of much of the X-ray emission we observe from quasars. How does the corona get so hot? It's probably heated by magnetic processes, reconnection events, wave dissipation, turbulent cascades. The details are murky, but the basic idea is that energy from the disk is channeled into the corona via magnetic fields, heating it to extreme temperatures. The hot electrons in the corona Compton scatter photons from the underlying accretion disk. Low-energy optical and ultraviolet photons from the disk are boosted to X-ray energies when they interact with the hot electrons. This process, inverse Compton scattering, is very efficient at producing X-rays. The resulting X-ray spectrum has a characteristic shape. There's a power law component from the Comptonization process, and there's often a reflection component. X-rays from the corona that hit the disk get partially absorbed and re-emitted, and then travel to us carrying information about the disk's composition and ionization state. By studying the X-ray spectrum in detail, we can learn about both the corona and the disk. The power law slope tells you about the temperature and optical depth of the corona. The reflection features, emission lines of iron and other elements, tell you about the disk's composition, density, and how close it extends to the black hole. Some quasars show very strong relativistic reflection features. The iron emission line, for example, is broadened and distorted by Doppler shifts, gravitational redshift, and relativistic beaming effects from the inner disk. The line profile contains information about the black hole's spin, the disk's inclination, and the geometry of the emitting region. Spin is particularly interesting. Black holes can rotate, and their spin affects the structure of space-time around them. A rapidly spinning black hole drags space-time around with it, frame dragging, and this allows the accretion disk to extend closer to the event horizon than it could around a non-spinning black hole. By measuring the inner edge of the accretion disk from the iron line profile, we can estimate the black hole's spin. Some quasars appear to have rapidly spinning black holes, with spins close to the maximum allowed by general relativity. Others have lower spins. The distribution of spins tells us about the black hole's formation and growth history. If a black hole grows primarily through steady accretion from a coherent disk, it should spin up over time, approaching maximum spin. If it grows through chaotic accretion from random directions, or through mergers with other black holes that might have been spinning in different orientations, the final spin could be lower. The observations suggest a mix. Some black holes are near maximum spin, some are not. This is consistent with a picture where different black holes have different growth histories. Some grew through steady accretion, others through more chaotic processes. Let me tell you about changing look quasars, because they're one of the most intriguing recent discoveries. For decades, we thought quasars changed on relatively predictable timescales. Brightness variations on days to years, fine. Transitioning from an active state to dormancy over millions of years, sure. But the basic type of the quasar, whether it showed broad emission lines or not, was assumed to be set by orientation, as the unified model suggests. Then we started finding quasars that change type on human timescales. A quasar observed in the 1980s showing strong broad emission lines is re-observed in 2010, and the broad lines have disappeared. It's transitioned from type 1 to type 2, or the reverse. A type 2 quasar suddenly develops broad lines and becomes type 1. This shouldn't happen if type is just about viewing angle. The torus isn't moving, our perspective isn't changing, so what's going on? The answer appears to be that the accretion state itself is changing. When a quasar's accretion rate drops significantly, the broad line region might be disrupted or disappear entirely. The fast-moving clouds close to the black hole need to be sustained by the disk's radiation field. If the disk dims, the clouds might dissipate or move outward. The broad lines vanish not because they're hidden, but because they're not being produced. Conversely, if the accretion rate increases, the broad line region can reform. The disk brightens, ionizes gas in the vicinity, and the characteristic broad lines reappear. Changing look quasars are teaching us that the accretion process can be more variable than we thought. Dramatic changes in accretion rate can happen on timescales of years, not just millions of years. The quasar's appearance can fundamentally change within a human lifetime. This has implications for how we classify and count quasars. If a significant fraction can switch between type 1 and type 2 states on short timescales, then our surveys, which are typically snapshots in time, might be misrepresenting the true population. It also raises questions about what triggers these rapid changes. Is it a sudden influx of fuel? A star or gas cloud falling into the central region? Is it an instability in the accretion disk that temporarily shuts off the flow? We're still investigating, and here's something that will make you uncomfortable. We don't fully understand the structure of the accretion disk itself at the most fundamental level. The standard model, the Shakura-Sunyaev thin disk, makes simplifying assumptions. It assumes the disk is geometrically thin and optically thick. It parameterizes the viscosity with a fudge factor called alpha. It assumes the disk radiates as a multi-temperature blackbody with the temperature decreasing as you move outward from the black hole. This model works remarkably well for explaining the overall properties of quasar emission. The predicted spectrum matches observations reasonably. The scaling relationships between black hole mass, accretion rate, and luminosity come out right, but the details don't quite work. The disks appear larger than predicted, as I mentioned with microlensing. The temperature profiles might be different. The viscosity mechanism, the magnetorotational instability, is more complex than the simple alpha prescription captures, and the model doesn't naturally incorporate magnetic fields, winds, or coronae, which we know are present. More sophisticated models exist. Radiation magnetohydrodynamic simulations can model disks with fewer assumptions, tracking the evolution of magnetic fields and radiation fields self-consistently. These simulations are computationally expensive. They require supercomputers running for weeks, but they're revealing complexity that the simple models miss. For example, simulations show that disks can develop strong winds driven by radiation pressure and magnetic forces. Matter doesn't just spiral inward, some of it is blown outward, escaping the system entirely. This means the accretion rate at the outer disk might be higher than the accretion rate at the black hole. Matter is being lost to winds. Observations are starting to confirm this. We see outflows in many quasars, sometimes carrying away significant fractions of the total mass that's trying to accrete. The black hole isn't capturing everything that falls toward it. Some escapes, and that escaped matter carries energy and momentum into the surrounding galaxy, contributing to feedback. The structure of the inner disk, very close to the black hole, is particularly uncertain. General relativistic effects dominate here. The disk is orbiting at substantial fractions of light speed. Frame dragging is significant. Photons emitted from the disk can be bent by the black hole's gravity, some even orbiting multiple times before escaping or falling in. Modelling this requires general relativistic radiative transfer, tracking how photons move through the curved space-time near the black hole, accounting for all the relativistic effects. It's computationally challenging, but necessary for interpreting observations of the inner disk. The iron emission line I mentioned earlier is one of the key observables. Its precise shape encodes information about the disk's geometry and the black hole's spin. But extracting that information requires accurate models of how the emission is produced, how it propagates through the disk, and how relativistic effects distort it before it reaches us. We're getting better at this. Modern X-ray telescopes have the spectral resolution to measure the iron line profile in detail, and our models are sophisticated enough to fit the data and extract physical parameters, but there's still uncertainty. Different modelling assumptions can give somewhat different results for the black hole's spin or the disk's inclination. This is normal in astrophysics. We're studying objects we can never visit, using indirect observations, building models that require simplifying assumptions. The remarkable thing is how much we've learned despite these limitations. Let me bring us toward a conclusion for this section by talking about the future of quasar studies. The next generation of telescopes will transform the field. The extremely large telescope, when completed, will have a 39-metre primary mirror. That's an order of magnitude more collecting area than current large telescopes. It will be able to take spectra of faint, distant quasars in a fraction of the time currently required. The Square Kilometre Array, SKA, will be the world's largest radio telescope, with a collecting area of a square kilometre spread across thousands of individual antennas. It will detect radio emission from quasars across cosmic time, mapping the evolution of jet activity and radio-loud quasar populations. The Vera Rubin Observatory, which should begin operation soon, will survey the entire visible sky repeatedly, building up a dynamic map of the universe. It will discover thousands of new quasars, track their variability, identify changing look systems, and find rare outliers. And JWST is already delivering. Its infrared sensitivity is uncovering dust-obscured quasars, probing the early universe, finding black holes at epochs when they shouldn't yet exist. Each new JWST result seems to challenge our models in some way, which is exactly what we want. Challenges drive progress. Future X-ray missions will have better sensitivity and spectral resolution than current satellites. They'll measure relativistic reflection features with unprecedented precision, constraining black hole spins and disk geometry. They'll study the corona in detail, testing models of how it's heated and how it produces X-rays. And someday, probably not in the immediate future but within decades, we might have space-based interferometers capable of imaging quasar accretion disks directly. Imagine seeing the spiral structure, the hotspots, the inner edge of the disk, the base of the jets. Imagine watching in real time as material spirals inward and crosses the event horizon. That's not science fiction. It's engineering. The physics allows it. We just need to build the instruments. Every observation will sharpen our understanding. Every new data set will test our models. Every outlier will force us to reconsider our assumptions. And through all this, the quasars themselves remain unchanged by our scrutiny. They existed billions of years before we evolved the capacity to observe them. They'll continue shining or fading according to the laws of physics, indifferent to whether anyone is watching. But we are watching. We've gone from discovering quasars as mysterious points of light to understanding them as supermassive black holes with accretion disks. We've measured their masses, their distances, their luminosities. We've mapped their structure using clever techniques. We've connected them to galaxy evolution and cosmology. The journey from ignorance to understanding has taken 60 years. Multiple generations of astronomers building on each other's work, thousands of papers published, millions of hours of telescope time, entire careers dedicated to unraveling the nature of these cosmic engines, and we're not done. We're still learning, still discovering, still refining our models. The quasars are patient teachers. They don't hide their nature. They broadcast it across the universe in photons of every energy. They leave signatures in the spectra, patterns in the variability, clues in the correlations. Our job is to collect those clues and assemble them into understanding. We've done well so far. We understand the basics. The mechanism is clear. The physics, while complex, is tractable, but the extremes still await. The records, the outliers, the quasars that define the boundaries of what's possible. Those will be the subject of our next exploration. The brightest quasars ever observed. The most distant, showing us the universe in its infancy. The most massive black holes, the fastest growing, the strangest configurations, objects with names and coordinates, specific systems that challenged our understanding and forced us to expand our models, quasars that broke records and set new ones. We'll talk about their role in cosmic history, how they reionized the universe, how they shaped the large-scale structure, how they regulate the most massive galaxies, and we'll confront the puzzles they present, the ones that exist earlier than they should, the ones brighter than physics easily allows, the ones that make us question whether we really understand black hole formation and growth. But that's for next time. For now, rest with what we've covered. You understand what quasars are: supermassive black holes feeding on infalling matter through turbulent magnetized accretion disks, engines of tremendous power operating at the limits of efficiency, objects that connect to galaxy evolution, cosmology, and the large-scale structure of the universe. You've learned about the observations, spectroscopy, variability studies, multi-wavelength campaigns, reverberation mapping, microlensing. The techniques we've developed to study objects we can never visit. You've learned about the physics, accretion, jets, feedback, magnetic fields, radiative transfer, relativistic effects, the complex interplay of processes that makes quasars what they are. And you've glimpsed the frontiers, the questions we're still working on, the observations we're still trying to explain, the models we're still refining. This is science in action. Not a finished edifice of perfect knowledge, but a growing, evolving understanding built on observation and theory in constant dialogue. Sleep now. Dream of accretion disks spiraling around invisible singularities, of jets launched at near light speed, carving through the cosmos, of photons emitted billions of years ago carrying messages from the deep past. The quasars are out there right now, shining in the darkness, feeding, radiating, shaping their environments, and we've learned to read their light, to decode their secrets, to understand their nature. It's one of humanity's great achievements, the decipherment of quasars, from mystery to mechanism. And soon we'll talk about the champions, the record holders, the extremes, the brightest lights in all of cosmic history. Rest well. The universe revealed its secrets slowly. For billions of years, quasars shone in the darkness, their light travelling across expanding space, and no one was there to witness them. No telescopes, no observers, just photons on their endless journeys through the void. Then, in a small corner of one galaxy, on the surface of a rocky planet orbiting an ordinary star, a species evolved the capacity for curiosity, for wonder, for the systematic investigation of nature. We built telescopes, we pointed them at the sky, and we found lights that shouldn't exist. The discovery of quasars is a testament to what happens when observation meets theory, when data meets imagination, when confusion eventually yields to understanding. We went from detecting mysterious radio sources to comprehending the most powerful engines in the universe. From bewilderment to insight, from wondering what these objects could possibly be, to knowing they're supermassive black holes feeding on matter. That journey took 60 years, multiple generations of scientists, thousands of papers, millions of telescope hours, failed theories discarded, successful models refined, observations that confirmed predictions, observations that defied them and forced new thinking, and, through it all, the quasars remained what they always were. Accretion disks around black holes, physics in action, the universe demonstrating what's possible when gravity encounters matter at cosmic scales. You know now what quasars are. You understand the mechanism, the supermassive black hole, the infalling matter forming a disk, the friction and magnetic turbulence that allows accretion, the conversion of gravitational potential energy into radiation, the jets launched from near the event horizon, the feedback that regulates both the black hole's growth and the host galaxy's evolution. You know about the observations, the spectra that revealed enormous distances, the variability that showed compact emission regions, the multi-wavelength campaigns that mapped the structure, the clever techniques, reverberation mapping, microlensing, interferometry, that let us probe scales we cannot directly resolve. You know about the diversity, quasars, Seyfert galaxies, radio galaxies, blazars, all the same phenomenon viewed from different angles and at different activity levels. The unified model that brings order to the zoo of active galactic nuclei. You know about the challenges, the feeding problem, the formation of supermassive black holes in the first place, the details of jet launching and collimation, the structure of the accretion disk's innermost regions where general relativity dominates. This is real knowledge, hard-won, built on decades of careful work. It's not speculation or guesswork, it's physics grounded in observation, tested against data, refined through the scientific process. But knowledge is never final. Every answer generates new questions. Every observation reveals new complexity. The more we learn about quasars, the more we realise how much remains to be understood. And that's exactly as it should be. Science isn't about reaching a destination where all questions are answered. It's about the journey of discovery itself, the perpetual pushing at the boundaries of what we know. The next phase of that journey, the exploration of the extremes, the records, the role of quasars in cosmic history, awaits. We'll talk about specific objects that challenged our understanding, the most distant quasars found by JWST, the most luminous ever observed, the black holes growing faster than they should, the systems that reionise the universe and shape the cosmic web. But those stories deserve their own telling, their own space to breathe and expand. They're waiting for you when you're ready to continue this exploration. For now, close your eyes knowing you live in a universe where such things exist, where supermassive black holes feed and shine, where the most efficient engines permitted by physics operate at the centres of galaxies, where light from billions of years ago carries information across cosmic distances to telescopes on Earth. You live in a universe we've learned to understand, not perfectly, not completely, but genuinely. The quasars are no longer mysteries. They're phenomena we've decoded, processes we comprehend, objects we continue to study with ever greater precision. From mysterious radio sources to understood astrophysical systems, from confusion to clarity, from wonder at the unknown to wonder at the known. That's the achievement. That's what 60 years of quasar astronomy has given us. Sleep now. Rest well. Let these ideas settle into the deep places of your mind where understanding lives. The quasars will still be there tomorrow, shining across the cosmos, waiting to reveal more of their secrets. And when you're ready, we'll continue our journey together, into the records, into the extremes, into the cosmic history that quasars have written in light across the universe. The brightest objects in existence are patient. They've waited billions of years already. They can wait a little longer. Until next time.